Hello everybody, my name is Eline Radstake. I'm a PhD student of the Belgian Nuclear Research Center and I'm investigating the effects of spaceflight on the brain and on the skin. I'm very happy to be given the opportunity to present to you today a part of my research, which is on the development of an in vitro model to unravel potential interplay of simulated spaceflight stressors on the skin. When I talk about these spaceflight stressors, I'm mostly talking about the difference in gravitational level, the increased levels of ionizing radiation, as well as psychological stress that we see in space. These spaceflight stressors have short-term as well as long-term effects on the health of astronauts. For instance, when astronauts are being exposed to microgravity, they often show symptoms of space motion sickness. However, after a few days, these symptoms disappear, which indicate an adaptation process of the central nervous system to this microgravity environment. But when astronauts are being exposed to this microgravity for a longer period of time, we see deterioration of multiple physiological systems. For instance, in the musculoskeletal systems, where we observed increased signs of aging after exposure to microgravity. For the ionizing radiation, we need to distinguish between solar particle event and galactic cosmic rays. The radiation that astronauts are exposed to during solar particle events is relatively easily to shield from. However, the shielding becomes much more difficult, if not impossible, for galactic cosmic rays. These highly charged particles interact with the cells, and chronic exposure leads to increase in risk for multiple diseases. Then for the psychological stress, when an individual is exposed to a threat, the adrenal glands release adrenaline and cortisol, and this puts you in a fight or flight mode with the goal to increase the survival of increase the chance of survival of the individual and to restore allostasis. However, when you are exposed to this cortisol for a longer period of time, it's becoming maladaptive and it's been linked to several illnesses. Most space research the data that we have of space research now is coming from ISS studies, which are relatively close down to Earth, and the duration of these studies is usually 6 months with a few expectation of longer missions. However, when we want to go to the moon or to Mars, astronauts will be exposed to the spaceflight environment for a much longer period of time. And this really asks for a need of development of effective countermeasures and to be able to counteract the effects we see of prolonged exposure to this spaceflight environment. So why should we look at the skin? And the first and foremost reason is that the skin is the largest organ of the body. It consists of 3 layers. The outermost layer is called the epidermis. It's followed by the dermis and the hypodermis. And this is also represented in this cross-section. So again, we see the outermost layer, the epidermis, and the dermis. And inside the dermis, we find the fibroblasts, which are probably the most important cells of this skin layer, because they are the construction workers of the skin. And this means that they construct the extracellular matrix proteins of elastin and collagen, which gives the skin elasticity and strength. The skin holds some vital functions. It is a barrier. It protects our insides from threats from the outside, for instance, from mechanical forces, as well as differences in temperature. Furthermore, it has some functions as immune defense, sensory functions, and endocrine functions. In space, astronauts most frequently report little incidents related to skin. For instance, they have a lot of dry skin and rashes, but they also see small injuries and delayed wound healing when they are exposed to the spaceflight environment. And this led researchers to investigate further what happens to the skin during long-term spaceflight. So when comparing pre- and post-flight data after long-duration spaceflight, researchers found a thinning of the epidermis, so the outermost layer of the skin, up to 20%. And this was after a 6-month mission. So you can imagine the effect of this thinning of the outermost layer of the skin when space missions would be much longer when we, for instance, go to the moon or to Mars. What they also found is increase in collagen to elastin ratio. So remember, these were the extracellular matrix proteins in the dermis. A loss of elasticity of the dermis, as well as atrophy of the dermal matrix, which is very nicely represented in these figures. Here we see the skin again with the outermost layer, the epidermis, and this thicker layer, which is the dermis. And this is a pre-flight echography. And after long duration space flight, you can see here are several low echo zones, which indicates atrophy of these dermal matrix. And all the observed differences in skin after spaceflight are also related to skin aging. And to better investigate what will happen on the long term to the skin, researchers have also sent mice into space. Mice spent 3 months in orbit, which may not seem that long, but in human years it would represent approximately 7 years in space. And after this period in space, they found a reduced thickness of the dermis. This you can see in this figure. So this, again, a cross-section of the skin with the outermost layer on this side. And in this picture, you can nicely see that the space-flown mouse compared to the ground control have much thinner layer of the dermis here. What you also see is an increase in these hair follicles, which in the space-flown mouse, which can lead to an underestimation of the loss of dermal tissue in these mice. Another incident in which problems to the skin were reported has been recently shown in a case report. In this case, the astronaut spent a year in space, and when he returned, he had some severe sensitivity in the skin in gravity-dependent areas. And because of these increased sensitivity, the astronaut had to interrupt some of his post-flight activities. And this highlights also the need for developing effective countermeasures, because if we would want to go to Mars, when we arrive, we should be able, the astronauts should be able of handling their post-flight activities on their own. So we really need to find ways to counteract the effects that we see in the skin after long-term space flight. Unfortunately, these space studies done in the ISS have some limitations. For instance, the sample sizes are very small. There are not that many astronauts. And also the animals that are flying into space, the sample sizes are small due to the restrictions in space available. Furthermore, these ISS missions, as I previously said, they are usually 6 months. However, interplanetary space missions would take much longer than that. And also in these interplanetary space missions, the radiation field would look much different. That's why we need to develop in vitro models here on Earth to investigate cellular responses to this combined spaceflight environments, and to be able also to develop effective countermeasures. So what we have done, we have developed an in vitro simulation model to be able to expose cells to this combined spaceflight environment. For the skin research, we've used human primary dermal fibroblasts. So remember, the fibroblasts were the construction workers of the skin. And we have exposed them to microgravity using the random positioning machine. We irradiate them. We use different qualities of ionizing radiation. And we expose them to psychological stress by incubating the medium with cortisol. One aspect that we were very interested in is the delayed wound healing that we see in space. And wound healing is a very complex multicellular process. It consists of several phases. So when you first have the wound, you have the hemostasis phases in which the blood stalls at the after injury, the blood clot forms and the wound is being closed. Afterwards, you have an inflammation phase in which cells of the immune system, they travel to the site of the wound to remove pathogens and to attract other healthy cells. And once the healthy cells arrive, the proliferation phase starts, in which the cells start to proliferate and remodel the extracellular matrix. And these phases are very dependent on several biochemical factors. I will not go into detail on this now. But keep in mind that there are a lot of factors that can intervene with this wound healing process. And furthermore, the proper wound healing is also dependent of gravitational and mechanical forces at the cellular and the tissue level. So as I said before, astronauts report a delayed wound healing in space. And all these factors that we see that influence proper wound healing, if one of these factors is interrupted, there can be a defective repair. And the role of the fibroblast during wound healing is very significant. The most important roles during wound healing is migration, as well as the formation of the extracellular matrix. So after migrating to the site of the wound, the fibroblast starts modeling new collagen. And it starts first with making type 3 collagen, which is a sort of intermediate solution for restoring the extracellular matrix. Afterwards, the type 3 collagen is being broken down and replaced with type 1 collagen, which is a more robust type of collagen. So the fibroblast migration to the wound site and the interaction with the extracellular matrix is a very crucial process in wound healing. And we wanted to investigate how the simulated spaceflight environment intervenes with this migration and remodeling of the extracellular matrix by the fibroblast. And to investigate the migration, we have used an in vitro scratch wound assay. So we used an in vitro scratch wound assay in which we make a scratch in the cell monolayer. And then we monitor how the cells migrate back into the scratch. So as we can see here, we have the cellular layer. And the cells are starting to migrate into this wound. So if we then investigate how the spaceflight stressors intervene with this migration process, we can see that psychological stress has a significant effect on this migration ability of the fibroblast. So we have the relative wound closure of the fibroblast, which is a measure of migration over time. We have here the control condition in which the fibroblasts are not being exposed to any stressors. And with an increase of concentration of cortisol in the medium, we see a delayed migration of these fibroblasts. And when we expose the fibroblasts to ionizing radiation, we used X-rays in this case, we did not observe this delay in wound healing if we look at space-relevant doses. Furthermore, other researchers have also indicated that after microgravity exposure for 48 hours, fibroblasts also show a delayed migration. So compared to the ground control, so the 1G exposed fibroblasts, which after 48 hours are around 60% of wound closure, the microgravity exposed fibroblasts are still behind. Then we wanted to look at the collagen expression of the fibroblasts. We have investigated the expression of type 1 pro-collagen of fibroblasts exposed to the simulated spaceflight stressors. And again, we see a significant effect of psychological stress on the expression of this pro-collagen. So again, we have the pro-collagen expression on the y-axis, the control condition in which the cells have not been exposed to stressors, and the lower and higher concentration exposure of cortisol. And from this figure, you can clearly see that this exposure to cortisol reduces the expression of type 1 pro-collagen. And again, for the X-irradiated fibroblasts, we don't find an effect of on collagen expression on this space-relevant doses. We also see that gravity has an effect on the expression of collagen. You can see here, microgravity, the expression is much higher, and with the increase in gravitational load, the expression of collagen goes down. So in conclusion, we see that psychological stress has a huge effect on the migration as well as the expression of collagen in the fibroblasts. But with the X-irradiated fibroblasts, we don't really see this effect. Furthermore, if we in the future will include microgravity, we expect to find more severe interaction effects between the spaceflight stressors on the migration and the expression of collagen in the fibroblasts. Besides the extracellular matrix proteins, the cytoskeleton also plays an important role in migration of fibroblasts. In the schematic, you can nicely see the actin cytoskeleton, which is being heavily remodeled as the fibroblast is migrating in this direction. We have also exposed fibroblasts to microgravity, and after using the random positioning machine, and after 6 hours on this machine, we can see that this actin cytoskeleton, which is very important for migration, is remodeled. So in this picture, we have the 1G control condition, and you can nicely see the red actin fibers here. After 6 hours of microgravity exposure, you can see heavily remodeling going on in this actin cytoskeleton, which in the end could have an influence on the migration capability of these fibroblasts. Another example of measuring the effects of spaceflight environment on cellular mechanisms is measuring the DNA damage. Exposing cells to ionizing radiation leads to DNA damage, and galactic cosmic rays especially are highly ionizing along that tract, and they lead to more complex DNA double-stranded breaks. And we can measure these double-stranded breaks using an assay of phosphor-related H2AX molecules, and to indicate the DNA damage after the combined exposure. And we were able to indicate a significant interaction effect between the spaceflight stresses of ionizing radiation and psychological stress. Here we see a measure of the DNA damage as function of the dose given by X-rays in this case. Again, we have a control condition, and after incubation and with stress hormones and exposure to ionizing radiation, we see an increase in the amount of double-stranded breaks. So that were the most of the results I wanted to share with you today. We are currently still developing microgravity, and I hope to have some more data on that soon. With the inclusion of the microgravity, we will be able to complete the simulated spaceflight environment. And furthermore, in the future, we will also expose the fibroblasts to different qualities of radiation, for instance, also to iron and carbon. With the slides, I would like to end my talk. With this model, we will be able to better assess the risk related to deep space exploration missions. We will get more insight into the possible interaction effects of the different spaceflight stressors, and we hope to reveal possible mechanisms for the development of countermeasures. Thank you very much for your attention. If you have any questions, please do not hesitate to contact me. You can find my email address here, or approach me on the conference.